This is a lesson about the vector equation of a plane. I'm going to start with the vector equation of a line. So here's a set of 3D axes, the x coming towards me here, the y going across that way, and the z going vertically at the back. Here's the origin set inside that axis. And I've got a point from the origin and then another vector defined from that point. This is an indication of the vector equation of a line. R equals A takes me from the origin to point A, which is my point on the line, plus TB. Well, if this vector here is my vector B, the direction vector of the line, so if I went from the origin to point A and then travelled as many units as I liked in the direction of B, it would keep me on that line there. So I'll try to demonstrate that now by writing the equation of the line in vector format. I know that this vector here, my A, is 1, minus 1, 1. So that's my point on the line. I know that the direction of the line is 1, 2, minus 1, because I chose it to be that way. So if I enter the equation of the line as 1, minus 1, 1, plus lambda into 1, 2, minus 1, what we should get is a straight line which passes through this point here and has this direction. And there we go. So there's my R is A plus TB. But what happens if instead of having a linear factor of one vector, B, we move to a combination of two vectors, B and C? So if I change that equation to R is A, that's obviously going to take me to point A, and then whatever combination I like of vectors B and C. So here we are, 3D axes again, x coming towards me. R is A, takes me along the red vector to that point there. So in this case that's 1, 2, 3, so that's my point on whatever we're going to end up with here. And I'm saying I can have any combination I like. I can have 3 lots of this vector or minus a half lots of this vector and so on. So any combination I like of 1, minus 2, 1 with 1, minus 1, minus 2. So for example, I could choose to go to the end of the red vector and do 0 lots of the green one and 1 lot of the purple one. It would take me to here. I could choose to go to the end of the red vector and do 1 green one and 1 purple one. It would take me to here. I could choose to go to the end of the red vector and go minus 1 green one and minus 2 purple ones would take me up to here somewhere. So if I investigated every possible combination of those two, I would end up with this vector equation. I would say, let's see what happens if I go to 1, 2, 3. That's taken me to the end of the red vector. And then I go through every possible combination of 1, minus 2, 1, plus 1, minus 1, minus 2. And what I find is I've got a plane, a surface, a two-dimensional surface, which passes through the point 1, 2, 3, which was at the end of the red vector, and I can get to anywhere on this plane by doing some combination of the green vector and the purple vector. So maybe minus 1/10 of the green vector plus 3 times the purple vector would take me down to there. Okay. So we've introduced the idea as the vector equation of the plane as being just what we get if we start with the vector equation of the line but allow ourselves to move in 2 dimensions from the point A rather than just one direction. So now we look at the algebra. This is what we had before. R is A plus lambda B plus mu C. Gives me the equation of a plane, where A takes me from the origin to a point which is in the plane, and then some combination of B and C will allow me to move around within that plane. That's the most basic and slightly clumsy way of finding the equation of a plane. The next step on is to notice that if I use B and C and take the cross product of them, I will get a vector which is perpendicular to both B and C. Well, if B and C both lie in the plane, then something which is perpendicular to both of them must be normal to the plane. So it would look something like this. So B cross C would give me a new vector, n, which is normal to the plane. Now, if my point R is going to be in the plane, then what R minus A represents is the vector between my point and point A. And if my point is in the plane, then the vector between me and point A must be at 90 degrees to something which is at 90 degrees to the plane. So in other words, moving from me to point A in the plane must be perpendicular to the normal to the plane, so the dot product of the two of them must equal 0. So there's a second way of writing the equation of a plane. R minus A dot n equals 0, where A, the same as it has in everything you've done about vector equations of line, represents a point in the plane, and n represents the normal to the plane, which can be found from the cross product of two vectors that are in the plane. Now the next way of dealing with it is if I multiply those two brackets out, this will become tidied up slightly. I get r dot n equals a dot n. Now A is a point in the plane which I know, and n is the normal vector to the plane which I know. So there's nothing to stop me from just dealing with this dot product here. And we know that the dot product is probably known as the scalar product. So it's going to give me a scalar. So this is just going to be a number on the right-hand side. So I might have something like r dot 371 equals 5. That would be an even more efficient and elegant way of defining the equation of the plane, where this vector represents the normal. And although you don't know why, actually this number here is quite useful as well, because if you take that number and divide it by the magnitude of the normal, what you get is the shortest distance, in other words, the perpendicular distance between the plane and the origin. So here is another format for the equation of a plane. R dot n equals P, where the P came from any point in the plane dotted with the normal to the plane. Now finally, to get from this vector equation of the plane to a Cartesian equation of the plane, remember that R really stands for just any general point, x, y, and z, and n has components because it stands for the vector which is normal to the plane. A dot product means you multiply x, the top line by the top line, middle line by the middle line, and so on. So if I multiplied this out, I'd get n1 lots of x plus n2 lots of y plus n3 lots of z equals my number p. So here is a Cartesian equation of the plane, like this, for example. So again, a quite straightforward and simple way of defining a plane now. And we know that these three coefficients actually came from the normal to the plane. So I can jump straight between that Cartesian equation and a vector equation by knowing that the normal to this plane would have been 3, 2, 1. And also, should it be asked for, I can take another shortcut, and I know that that number divided by the magnitude of the normal, so in other words 7 over root 14, gives me the shortest distance between the origin and my plane. So this is something like what this plane would look like. 3x plus 2y plus z equals 7 is the equation of the plane. That means that the normal vector to it would be 3, 2, 1, and the shortest distance between it and the origin would be 7 over root 14.